Okay. Good afternoon. I am Roger Falcone. I'm from the physics department, and I'm very pleased to welcome and host my friend Ferenc Krausz on his visit to Berkeley. He's been here for 2 days, and during that time we've connected Ferenc with Berkeley researchers in many areas of his interests, of his many interests. And these are advanced spectroscopies for ultra-fast physics and medical diagnostics, advanced lasers. And I hope that he found the visit as exciting as we did with him being here. So I've asked his and my colleague, Professor Steve Leone of the chemistry department, to formally introduce our speaker. So Steve.
Great, thank you, Roger. It's an extreme pleasure for me to introduce Ferenc Krausz. Ferenc is a Hungarian physicist. He started his educational career as an undergraduate at Attosecond University studying theoretical physics, and then moved into electrical engineering at the Technical University of Budapest. Slightly later, he got his PhD at the Technical University of Vienna. And then he progressed to a habilitation, associate professor, full professor. But now, he's a director at the Max Planck Institute for Quantum Optics in Munich, and a professor of experimental physics at the Ludwig Maximilian University in Munich. So, personal story. Ferenc Krausz developed isolated attosecond pulses in his lab by a very amazing merger of laser technology and atomic physics. Using stabilized lasers called carrier envelope phase stabilization, compressing the pulses to their shortest possible limits, and driving the process of high harmonic generation, he achieved the first isolated attosecond pulses known to the world. And it set the world on fire because of the imagination of what you could do with these to measure very short time processes. Ferenc was visiting Berkeley, and I think it was around the fall of 2009. And in the D level of Hildebrand, we discussed with Zhiheng Lo. He was a student just moving on to a postdoc in my group at the time. And Zhiheng had done transient absorption with extreme ultraviolet light from high harmonics. And Ferenc said, you should come to Munich and we should set up transient absorption to do an attosecond measurement. And Zhiheng Lo did it. He went to Munich. It was, again, an amazing gesture to offer a whole laboratory of equipment that had been used for photoelectron spectroscopy and allow some student to come and start to modify this. And there was a great success, achieving the first attosecond transient absorption measurements, which now has become very popular methodology. So I had this personal experience, and it was extremely enriching. The second big personal experience was last summer in Sweden at the Nobel Symposium on attosecond science and technology. Amazing people came and gave their most impressive talks and renewed for me the special relationship with Ferenc. So as you know, Ferenc won the Nobel Prize in October. It was extremely speedy for the Nobel Committee to act. He had a progression of prizes, the Wolf Prize, the BBVA, Foundation Frontiers of Knowledge Award from Spain. But the Nobel Prize is a capstone, and it inspires all of us, I think, to understand, why this is such an important field. It brings time to the forefront in all of our measurement science that maybe had been a little bit neglected. It was noticed in chemistry, but never really in physics. And it kind of inspires us to think about the shortest possible things we could measure and what that might mean. And it's all enabled by the laser technology as well. So I want to welcome Ferenc to Berkeley, and I'm really pleased with this impressive crowd. Love to hear your lecture.
Thank you, Roger. Thank you, Steve. Good afternoon, ladies and gentlemen, dear faculty members, dear students, dear guest researchers. It is, I have to say, it is a great honor for me to be here at a place which probably exhibits the highest number of Nobel laureates per square meter on its area, and I have to say that I'm just overwhelmed. Of course, I knew that from history, but nevertheless, to be exposed to this within just a few hours, chemistry department, physics department, I don't even know which one has to show more, but kind of comparable numbers in both, so better not compare. I'm truly overwhelmed, and I'm still in the process of digesting what I've learned and what I take with me in terms of new ideas, but not only new ideas, but actually new questions. And I'll come back to that in my lecture, that this is the first important thing we have to do in science and research, to find for ourselves the right questions. So I thank you very much for taking care of me and for giving me the chance to be here at this most famous place. And I would like to make a compliment not just to the world-class faculty here, to the world-leading faculty here in both physics and chemistry, but also to you, the world-class students being here. It was a most inspiring experience just to spend the last hour up there and being exposed to questions which, which I receive at very few places from students. So really, I'm sure this place has not only a great past, a great presence, but also a great future with such students. So, with my lecture, I would like to deliver an example for the eternal, I guess, eternal truth of Max Planck. The more delicate the details are by which we can follow nature on any path, the richer and more lasting will the gains be that we can draw from this perception. In my example, the delicate details will be electronic motions in tiniest dimensions in both space and time. One of the hopefully lasting gains will be the cost-effective probing of human health. More specifically, I will address how the new discipline of attosecond physics now opens the door to the world of subatomic motions of what else than electrons, and how these motions can actually be initiated, controlled, and captured by light, and how these motions can be exploited to actually control light, and this way provide the tools for the new discipline, attosecond physics. The interaction of electrons with light plays a pivotal role in advancing technologies, both existing technologies as well as actually spawning new technologies. I will present two examples, but it is most likely that other, maybe even more important ones are yet to come. The more precisely we are able, or we will be able to control electrons, light, and their interactions, the richer and the more lasting the gains will be that we can draw from this ability. This would be my recommendation for the take-home message for you today. Before we immerse in the world of electrons and light waves, I think it is worth remembering that these entities, namely electrons as a carrier of electric charge and light as electromagnetic wave, did not exist in the repository of human knowledge until less than 150 years ago. Until less than 150 years ago. I can just compare this with the history of humankind, from Homo sapiens, right? Within less than 115 years, or less than 150 years ago, we have no idea what electrons are, what light actually is. Groundbreaking discoveries of the late 19th and early 20th century laid the foundations of all technological advances that harness electrons, light, and their interactions. For instance, processing and transmitting information. It all began with Faraday's experiments on electrolysis, which together with independent hints that elementary substances are composed of atoms led to the conclusion that electricity must also be divided into elementary portions. After mounting evidence by Philip Lenard and others, it was a series of experiments by Joseph Thomson just briefly before the turn of the 20th century that shed light on the nature of carriers of elementary portions of electric charge. As you know, subatomic particles called electrons, negatively charged by convention, orders of magnitude lighter than the hydrogen atom. In parallel, Maxwell's theory and Hertz and Röntgen's experiments revealed that radio waves, light, visible infrared light, just as X-rays are all different manifestations of the same thing, electromagnetic waves. But why doesn't the electron lose energy upon orbiting the nucleus, positively charged nucleus, and propel into it, as it should by the laws of classical physics? Why does it actually fill a sphere that is by about 10,000 times bigger in diameter than the nucleus? The electron's wave nature and the linear relationship, equally importantly, the linear relationship between its wave number and momentum, these two postulates made by de Broglie delivers a simple explanation without even understanding Schrödinger equation and all the complex complexity of quantum mechanics. Just these two things. Electron is a wave with this relationship. Wave number is connected linearly to its momentum. These two things explain, at least qualitatively, why the electron fills all this volume. And it was so inspiring and convincing that it immediately inspired Schrödinger to postulate the equation for the evolution and the stationary states of the electron's wave function. And it was, I think, equally importantly, in my personal view, equally importantly, it was the probability interpretation of the wave function by Max Born, which resolved the paradox between the electron as an immeasurably small particle and the finite size, quite substantial size, of the electron as a wave. So Max Born postulated that the modulus squared of the wave function gives the probability with which the electron can be found in that particular volume in space, as depicted here for the simplest kind of possible situation for the ground state of the hydrogen atom by this green cloud up on the right side of my view graph. The wave mechanics of Schrödinger and Born revealed that subatomic motion can only emerge by exciting an electron from its ground state to a superposition of stationary states. The resultant temporal variation of the electron's probability density constitutes the closest analogy to classical motion, exemplified here by the dipole oscillations of the 1s2p superposition state in the hydrogen atom. 75 years later, after subatomic motion had been described in theory, it could be captured in real time, just on the turn of the new millennium. Two major discoveries at the middle of this 75-year time span have been obviously decisive for the emergence of this technical capability. One is certainly well known to you and self-explanatory. The laser demonstrated by Mayman, utilizing the concept of stimulated emission, as you all know, discovered by Towns, Prohorov, and Basov. The other one is probably less known, but for developing the capability of capturing subatomic motion turned out to be, I would say, equally important. And this is the theoretical prediction of Keldysh that ionization by electron tunneling may occur with substantial probability within the half-wave period of a sufficiently strong, and I should say sufficiently slowly oscillating optical field. Based on these two major milestones occurring in 1960 and 64, actually, interestingly, it's just symmetric around my birth date in 62. Based on these two, I'm just realizing it. Based on these two major milestones, several advances paved the way to the birth of attosecond science. One of them being the generation of intense near-infrared laser pulses carrying a substantial fraction of its their energy in a single oscillation cycle, which were first demonstrated in Vienna in the mid-90s in the framework of a multilateral scientific collaboration by drawing again on a Nobel Prize-winning concept of chirp pulse amplification by Gerard Mourou and Donna Strickland. I will not explain to you how this was done because I think it's more interesting what can be done with this. I will briefly refer to these pulses, single cycle laser pulses, single cycle waveforms, just to keep the talk as short as possible. Exposing noble gas atoms to such a single cycle field creates ideal prerequisites for the optical field induced tunneling predicted by Keldysh decades earlier, as you will see in a moment. Here you see what is supposed to happen according to Keldysh if an atom, the wave function wave function squared of the most weakly bound electron, which is depicted by this green curve, is exposed to a single cycle laser pulse, which is supposed to have a cosine-shaped waveform, which means that it has one single most intense half cycle in the center. Such a cosine-shaped waveform can liberate an electron wave packet from its bound state via tunneling ionization at its central peak of field oscillations. If the laser field is linearly polarized, the strong electric field drives the electron away from the atom along its straight trajectory. After a several nanometer excursion, it is pulled back by the next half cycle of the linearly polarized laser field to the vicinity of its parent ion, where it re-encounters the bound state portion of the wave function of the same electron. This is quantum mechanics. The electron, one electron can be split up. Part of it remains in the bound state that is depicted by this Gaussian-shaped curve near the nucleus, and the other part of the electron was released by tunneling ionization, made this excursion, and now is returning and re-encountering its bound portion, right? And now let's just play the movie fully and see what happens if this re-encounter occurs. Then this returning electron wave packet overlaps for a short period of time with the bound state portion of the wave function of the same electron, and via interference results in high frequency charge oscillations, basically a rapidly oscillating atomic dipole antenna. The higher the momentum of the electron returning after its brief excursion, the faster the resultant dipole oscillates, and the higher the frequency of the electromagnetic burst that this oscillating dipole emits. So basically, we can understand more or less on classical grounds, apart from the tunneling. That's, of course, a quantum mechanical phenomenon, but with that accepted, the rest, the motion of the electron in the strong laser field, and then the oscillation of this, or the emergence of this atomic dipole oscillations, this is basically something that can be understood on classical grounds. This is sufficient to understand actually how stronger laser field potentially results from this process in the emission of higher energy photons, because a stronger laser field transfers more energy to the electron. The returning electron has a higher momentum. The electron with a higher momentum passes through the bound state portion faster. Therefore, the dipole oscillates faster. A faster oscillating dipole radiates higher frequency radiation, so basically higher photon energy. So simple Newtonian and mechanics and Maxwellian electrodynamics provides insight into how tunneling ionization may imply the emission of XUV light with a duration that is likely to be a fraction of the half cycle of the driving laser field. Since the whole process is confined to less than a full optical cycle, and therefore it's highly likely that the actual re-encounter is confined to less than a half cycle. This would actually imply for a near-infrared laser field a duration of less than 1 femtosecond. To generate this XUV light, that's pretty straightforward. We expose just a bunch of neon atoms in this small tube to the single cycle laser pulses, this coherent XUV light emerges as a highly collimated coherent radiation depicted by this violet pencil there. What turned out to be more challenging and took several years and quite a few repeated attempts was the measurement of the temporal structure of this radiation. To this end, this radiation was focused with a double mirror on a second jet of, in this case, krypton atoms, and a separate small diameter mirror focused the XUV beam, and the bigger mirror the laser beam into this gas target, where the one could be delayed with respect to the other. And the XUV mirror actually band-pass filtered the highest energy photons from this high harmonic spectrum, as you can see on the inset. Basically, the reflectivity curve is indicated by this dashed violet line. So we just select the highest energy photons, and actually we see already on the spectrum that it seems that the harmonics coalesce, which is a first indication that this burst seems to be isolated and it's not being repeated every half cycle, which is behind actually the harmonic structure at lower photon energies. This was the setup with which Michael Henschel and Reinhard Kienberger actually obtained first experimental indication of the existence of sub-femtosecond XUV light. We could not really measure a very, very precise pulse duration. At that time, we could set a kind of upper limits, turned out to be 650 attoseconds, because the actual waveform of the single cycle light, which was used both for the generation and later for the measurement, was not well controlled. This waveform control came a couple of years later, and permitted the highly reproducible generation of isolated attosecond pulses in the precision metrology by implementing Paul Corcom's concept of a light field-driven streak camera. Here, the XUV pulse again hits krypton atoms in the presence of the laser field. We'll see it in a moment. We measure the flight time of those electrons which are being released, catapulted from the atoms parallel to the direction of the linearly polarized laser electric field. Depending on the moment of release, the electrons are accelerated or decelerated by the laser field, mapping the temporal profile of the XUV pulse to a final momentum distribution of photoelectrons, which is the green curve. Recording this XUV-induced and laser-streaked photoelectron spectrum as a function of delay results in a spectrogram. It's very much like a frog spectrogram in femtosecond technology. This spectrogram allows complete retrieval, just as a frog spectrogram. This spectrogram allows a complete retrieval of both the laser waveform and the complex amplitudes, both amplitude envelope and chirp of the attosecond XUV pulse. The experiments demonstrate actually how control enables observation, this time on an attosecond time scale, and renders the basic tools, the attosecond varying electric force of light and the attosecond duration XUV light available for real-time observation and control of electron light phenomena. With these tools in place, we can set out to perform attosecond time resolved spectroscopy, and that's indeed what we did after 2003, 2004, after these tools have been in place. And I just would like to give you one example, and it turns out to be actually my favorite example that originates from this very place, as Professor Leone just referred to that. Here was the idea born to extend the technology that he pioneered in the femtosecond domain, to extend this to the attosecond domain. And we devised the simplest possible proof of concept experiment for this. And we thought, well, let's see whether this technique is good enough and is suitable to actually visualize how optical field ionization, this arguably most fundamental strong field process, actually occurs in time. And maybe something else occurs afterwards, as we will see in a moment. So what we did was basically the same setup. Now this krypton gas, actually this plays two roles. On the one hand, we can do the streak camera measurement first, as is just demonstrated you, to know what our tools are like, right? I mean, what is the waveform of our single cycle pulse? What are the parameters of the XUV attosecond pulse? Then these very same krypton atoms change their roles, and they become the subject of a temporal interrogation in a slightly different setting, where we turned up the intensity of the laser pulse so strongly that they started ionizing the krypton atoms. For the streak camera measurement, the laser field is much weaker. The laser field doesn't, the atom doesn't even notice the laser field. The laser field is so weak. We need just a little field strength to give a kick to the freed electrons. That's what needed for the streak camera measurement. But if we turn up the laser intensity by a couple of orders of magnitude, then it becomes strong enough to ionize, as I showed you before, to do this optical field ionization. And that's exactly what we did. And basically the XUV pulse was used as a probe. Basically in the setting pioneered by Steve Leone in the femtosecond domain, but we have now an XUV pulse with a spectral width of more than 10 eV, which meant actually something like 250 attosecond pulse duration, right? So basically the exposure time of this ultra-fast camera was 250 attoseconds, basically dictating the time resolution. And basically we delayed this attosecond probe. Actually here you see the faces that Steve referred to, Ziheng Lo, Thomas Pfeiffer have been in his group at that time. Steve is here, of course. And they basically, Ziheng Lo and also Thomas Pfeiffer teamed up with Eleftherios Goural-Markis and his colleagues to realize this experiment. If we delay the attosecond probe, then all of a sudden, obviously, portion of the atoms have been ionized by the single cycle laser field, and obviously the ions in the ions, all of a sudden, some absorption line appears somewhere 78, 79 electron volt. And that's what we can measure as a function of delay with respect to the ionizing single cycle laser field. And the depth of this absorption depth is kind of proportional to the number of ions that have been produced by the strong field via tunneling ionization. And that's what we have evaluated as a function of delay. And here you see now the result in slow motion replay, temporal magnification 10 to the 15. You see how within the central half cycle, the ion population builds up within something like 700 attoseconds. There is a little bit of ionization also in the neighboring half cycles, but just a few percent. The main part of the ionization really is confined to the central half cycle. And here, a close kind of closer investigation and comparison with theory reveals that actually, interestingly enough, the ionization rate is slightly lower than predicted by Keldysh. And even actually the improved theory by Amosov, Delone, and Krajinov, ADK, even that could not fix the problem, so it's nothing to be fixed. Actually, it turns out that obviously from this measurement we see it for the first time that at this particular wavelength in the near infrared, this is the wavelength of the titanium sapphire laser, the field oscillates already too fast for the electron, for the tunneling electron, to be able to adiabatically follow the variations of the field. And that's what we see here. The red curve has a slightly smaller gradient as compared to the green, the theoretical prediction, which is based on the quasi-static approximation that basically the electron, the tunneling current instantly responds to the variation of the field. This would correspond to the green curve. So we see here basically experimentally that at 800 nanometer wavelength, optical field-induced tunneling happens in a non-adiabatic way. What is also interesting and important to mention that actually the electron is liberated with comparable probability from two different spin orbit quantum states of the 4p subshell of krypton. As a consequence, a hole in the electron cloud is created. Basically, the hole is created actually in a superposition state. And you remember I mentioned at the beginning of my talk that a superposition state means motion. And the recorded transient absorption spectra, these are the spectra as a function of delay between the ionizing laser field and the attosecond XUV probe, indeed exhibit a periodic variation with increasing delay of the XUV pulse with a 6 femtosecond period, which corresponds to the 0.7 energy electron volt energy separation of the two spin orbit levels. to actually develop the film from these transient absorption spectra captured with 150 attosecond exposure. The photographer's job is taken over by theorists modeling the interaction. And the good agreement between the theory and experiment allows to retrieve the attosecond snapshots of the whole density distribution, as well as, I think it's also very, very, very interesting and important, as well as the initial density distribution, which appears to be elongated along the laser polarization, somehow as intuitively expected. And here again, we can reconstruct the motion in slow motion replay, again with a temporal magnification of about 10 to the 15. I think it's interesting to point out that this magnifying power that we used here to actually make these subatomic motions perceivable to human observation corresponds to the spatial magnifying power, to the combined spatial magnifying power of a state-of-the-art electron microscope and a space telescope. This sounds, first hearing this sounds, I think, quite exciting, but I have to tell you that that expresses something rather disappointing. This actually conveys us that our eyes have a resolving power in time vastly inferior to that in space, right? We need basically 7-8 orders of magnitude bigger magnification in time to make subatomic motion visible. Then we need a magnifying power in space to allow us to observe atomic structure in space. To quote Eva Olsson, the chair of the Nobel Committee, we can now open the door to the world of electrons. Attosecond physics gives us the opportunity to understand mechanisms that are governed by electrons. The next step will be utilizing them. In order to be able to tackle real-world challenges, attosecond technology, so far relying on complex vacuum systems, must become simpler and more powerful. This was recently enabled by single-cycle light, owing to its ability to realize the same process in wide-gap solids that we just studied in atoms. Optical field-induced tunneling ionization. But why is actually confinement to a single optical cycle, confinement of the interaction to a single optical cycle indispensable here? Because no solid matter could otherwise survive the required critical field strength of about 2 volts per angstrom for a wide gap material that is required to actually induce this optical tunneling. For the experts to reach the regime where the Keldysh diabesity parameter becomes smaller than 1. This is this critical field strength. And if we realize such a field strength in a multi-cycle pulse, we would just destroy any solid material, right? So the only possibility, the only way of realizing such an interaction in a way that the sample survives the exposure to the pulse is to use a single cycle pulse. Tunneling is then largely confined to the central half cycle of the cosine-shaped waveform. We have just seen this, how this happens in an atom. The same way would this happen in a wide-gap semiconductor. In the tunneling, in that case, promotes electrons from the valence band to the conduction band. Right? In the atom, it just releases from the atomic bound state to a continuum state, positive and negative continuum state. Here, the same process, tunneling ionization, tunneling optical field-induced tunneling promotes the electron from the valence to conduction band. Sub-femtosecond carrier injection replaces or can replace sub-femtosecond XUV light and obviates the need for vacuum systems for a class of applications highly relevant for advancing electronics, attosecond control and probing of valence and conduction band carrier dynamics. In a primary step, sub-cyclic carrier injection is used for optical field sampling by implementing it in a small volume between two electrodes, where the test laser field depicted in blue here separates the injected electrons and holes. These electrons and holes are injected by this red single cycle laser field within its central half cycle, and this green curve shows here the temporal evolution of the injection, of the transition from the valence to the conduction band. So this test field separates these electrons and holes, and these separated electrons and holes form a giant dipole, and this giant dipole drives a current in this external circuit, which we can measure, and that's what you see here. And from that, we can retrieve the electric field evolution of the test field, in this particular case, basically a titanium sapphire laser pulse carried at 750 nanometer wavelength. And the green curve shows the result of the kind of gold standard attosecond streaking. So obviously the new technique, nonlinear photoconductive sampling, is working well. With its fidelity now also confirmed by attosecond streaking. The technique has recently proven its capacity to sample actually also deep UV fields beyond 1.5 petahertz. As shown here, you see that we can resolve half cycles that last only 500 attoseconds, indicating that our all-solid state light sampling instrument must have a resolution of 200 attoseconds or better. Light field sampling now provides a new probe for attosecond phenomena, the electric field of light from the infrared to the ultraviolet. It directly probes the arguably most fundamental consequence of any light-matter interaction, the displacement of electronic charge density in response to the incoming oscillating electric field. This response, this induced polarization, is imprinted on the electric field transmitted through the sample. Referencing this transmitted field through the input field allows for a thin medium unambiguous retrieval of the polarization response, the green curve here. And these two curves, the red and the green, the electric field and the induced polarization, determines the instantaneous energy flow from the light field into matter and vice versa, just given by this very simple formula. Electric field times actually current density. The temporal derivative of the polarization is current density. So basically, yeah, this is just one of the simplest formulas we remember from our undergraduate studies. And that's what you see here, basically integrated this energy density transfer from the field to the medium, integrated from a time point just before the laser pulse arrives in the sample for two different types of materials, for an insulator, in this particular case quartz, and a semiconductor, in this particular case silicon. When subjected to a linearly polarized single cycle near-infrared laser pulse. For the highest field strength, which are actually the blue or violet, blue curves up there. The energy transfer in both cases is irreversible, right? Because the curve remains up after the laser pulse is gone. So basically energy is transferred and remains in the medium. As a consequence of multi-photon induced or tunneling ionization assisted transitions from the valence to the conduction band. For reduced field strength, the energy transfer becomes fully reversible in the 6-photon band gap, a regime ideal for high-speed signal processing because this process just doesn't deposit any energy and therefore doesn't cause any heat dissipation, right? So basically this is where we want to realize optical signal processing, where no energy is left in the medium after the interaction. Interestingly, this regime doesn't occur in a 2-photon material where actually the reactive and dissipative nonlinearity always appears in combination. One is proportional to the real part, the other one to the imaginary part of chi3. Both are chi3 processes. These studies actually showcase how real-time access to the light-electron energy transfer explores optimum conditions for ultra-fast optoelectronic signal manipulation. Petahertz bandwidth field metrology relies on sub-cycle carrier injection, but we can utilize such a carrier injection in addition, in combination with petahertz bandwidth field metrology, and if we do so, we can gain sub-femtosecond control and can perform sub-femtosecond resolution interrogation of carrier dynamics. And that's what I would like to show you. This takes me maybe a couple of minutes, and then I would need maybe 5-6 more minutes for the last part, for the medical part, if it's okay. Yeah? For proving this concept, we sent a few cycle mid-infrared laser pulse carried at a wavelength of 2 micron through a silicon semiconductor sample. The transmitted field has been probed by our petahertz sampler. That's what you see here. And now we inject carriers into the sample first, way before the actual test field, the black curve arrives. And what happens is, as you see, the amplitude decreases, and more interestingly, the wave is shifted forward in time. Does anyone have any idea why the wave is shifted forward in time? We inject carriers into the material. So free electrons. Free electrons add a negative contribution to the refractive index. And this means that the real part of the refractive index. And if the real part of the refractive index is reduced, this means that the phase velocity increases. So basically, the wave travels through the medium faster, thanks to the presence of free electrons. So really, really nice textbook example of plasma physics. Now, more interestingly, what happens if the carrier injection appears in the center of the test pulse? Then the field doesn't change at all before the injection, for good reasons. There is no change here. But there is a clear, distinct change in the transmitted electric field after the injection, which is induced by the kind of free carriers that have been suddenly injected. And now we just zoom in on this change in the transmitted electric field caused by this sudden sub-femtosecond carrier injection. This is shown here. So we just replot this change, and now we zoom it again. So this is just much smaller than the previous amplitude. This is just a difference between the electric field without the injection and with the injection, right? This is the difference. And now if we shift this forward in time, the difference changes like this. So we see that right after the injection, the curves are different. but just for a few femtoseconds. Then they merge. So basically, there is a memory effect here. Basically, the polarization response is coherent with the injection within a few femtoseconds, which means over that period, the coherence is not destroyed by collisions. So we have ballistic transport, no collisions. And within a few femtoseconds, these differences disappear, and all curves look the same. So here we are in the range of ohmic charge transport. So we see here in real time how ballistic charge transport, dissipation-free ballistic charge transport, is turning into dissipation causing ohmic transport. Our ability to quantitatively measure the polarization response of matter to optical radiation uncovers the scale of the displacement of valence electron charge density in quartz, which is behind the nonlinear response. And remarkably, it is of the order of something like 0.1 picometer, a distance smaller than 1,000th of the diameter of an atom. And yet, this tiny subatomic motion is not only measurable, but may also serve as a basis for future petahertz rate electronics. So for the last few minutes, really just a few minutes, Attosecond, I would like to show you how Attosecond probing of picometer resolution electronic displacement is not only relevant for advancing electronics to its ultimate limits, but hopefully the same technical capability also provides access to minuscule changes of the molecular composition of human blood, particularly human blood plasma, which is a sensitive indicator of health disease transitions. To sense these transitions, we propose, instead of searching for individual biomarkers, actually accessing the global molecular landscape of human blood via field-resolved spectroscopy. We expose human blood plasma to a single-cycle infrared laser pulse which coherently excites molecular vibrations within its spectral band, within the spectral band of the excitation. The vibrating molecules in turn radiate coherent infrared waves in the wake of the excitation. This resultant signal is characteristic of the molecular composition of the sample. We capture this electric field molecular fingerprint with highly sensitive electro-optic sampling. This fingerprint signal is expected to change whenever some emerging abnormalities change the sample's molecular composition, which actually more or less each disease does some way. We have recently indeed verified this for several chronic conditions such as cancer, cardiovascular, and metabolic disorders. It's a prominent example. Just would like to show you one single example. We compared 470 samples of non-small cell lung cancer patients with the same number of samples of reference individuals free from cancer, briefly contrast, with the two cohorts being carefully matched regarding the distribution of the subject's age and other parameters. This is very important not to be fooled and not to measure actually those differences rather than something caused by the disease. These are the electric field molecular fingerprints of all samples. On this scale, we see little differences between the individual signals, but zooming in, for instance, some 1,000 femtoseconds, 1,050 femtoseconds after the excitation peak, where molecular emission already dominates over the excitation, clear differences between the two cohorts come to light. We can quantitatively analyze these differences in terms of the gaps between adjacent zero crossings of the oscillatory signal. We call them half-cycle gaps. And here you see the mean and the standard deviation of the half-cycle gap spectroscopic markers, something like 350 of them in this particular case, evaluated from the fingerprints of stage 1 to stage 4 lung cancer, non-small cell lung cancer, from the fingerprints of their controls, and more importantly, the differences between the two cohorts plotted here. So this is the controls, and these are the differences. Here we shifted these differences just to zero with respect to the mean of the controls. These cancer-induced changes in the half-cycle gaps range from tens to hundreds of attoseconds in the 350 spectroscopic markers. So basically, these are kind of equivalent to the up and down regulation of concentration of proteins or other molecules in blood, right? It's just another type of marker. It's a spectroscopic marker. The magnitude relative to the spread of the controls is referred to the effect size, shown in this small inset up there, which turns out to be to increase for progressing stages, and so does the actual classification efficiency, the so-called area under the curve. These AUC values, these classification efficiencies, are quite promising for non-metastasized lung cancer. However, they could be even further improved by reducing the spread of controls. Even at the current stage of development of infrared fingerprinting, by just reducing the spread of controls. Just imagine we would compare this not to a bunch of other people's, healthy people's fingerprint, which have a large spread, but to your own fingerprint collected before you have contracted this disease. The spread of your own fingerprints over time is much smaller, and if the spread is smaller, the detection efficiency increases. So in a longitudinal follow-up setting, if we would follow up people and would take a small blood sample from them year by year, and would start doing so whilst you are all healthy, then we can measure your personal baseline, establish the personal baseline of your personalized infrared fingerprint, and if we compare the lung cancer-induced change in the infrared fingerprint which we have measured in this study, then this would allow, at the present stage of development of the technology, to recognize an emerging cancer case at stage 1 with an efficiency above 90%. This is unprecedented. There is no such biomarker existing that could predict stage 1 lung cancer with this efficiency. Actually, we are performing such a study with 15,000 participants in Hungary currently. This Health for Hungary study, where we follow up people over 10 years, and unfortunately for the individuals, some 100, 150 people will contract lung cancer. Out of these 15,000 over the 10 years, some 300 will contract some severe cardiovascular disease, and some 500 will contract some sort of metabolic disorder, mainly diabetes. And once these diagnoses will be available, we can go back and look at the blood samples collected years before and check at how early stage the infrared fingerprints contain signatures of the disease to actually validate the approach, which could, if applied over the whole world, save 17 million people's life who have to die year by year at an age way below 70, where they shouldn't die, but they do because these diseases are recognized at a far too late stage. This actually led me to formulate two questions, and now I'm coming back. What is the most important part in our scientific career to find the right questions for ourselves? And it took me 61 years plus a few more months to formulate the right question for myself. And I can only hope that I have a few more years to actually address this question with my group, namely, can the molecular composition of human blood provide sufficiently comprehensive information to serve as a basis for populational health training. And can infrared and possibly ultraviolet electric field molecular fingerprinting make a contribution to accessing this information? These are the questions that I would like to continue to pursue with the AttoWorld team, along with an increasing number of collaborators from all over the world in the years to come. And at the same time, we also try to maintain the hopes of those who are already dreaming of joining in, like Vladislav here, from Lyceum number 10 in Marhanets in Ukraine, near the front line. We are supporting him with quite a few others, with all the more together who the more donations we can collect with our organization Science for People. And we do so because we believe that all these children, just as all other children anywhere else, deserve a chance to realize their dreams. Please support to allow us to extend our support to as many of them as possible. I guess we badly need all of them to carry on once our own time comes to an end. Thank you very much.